Humanity's fastest machine is already racing through space at impossible speed, and it still wouldn't reach the nearest star in your lifetime, not in your children's, not in your civilization's. This isn't a failure of technology. It's a limit built into reality itself, but hidden inside that limit is a loophole so extreme it breaks our intuition. A way for one human life to cross millions of light years while only decades pass. If that sounds impossible, stay with me, because the universe allows it and almost no one understands why. Let's begin. Right now, humanity's fastest creation is screaming through space at 430,000 miles per hour. At this incomprehensible velocity, you could circle Earth in under 4 minutes. Yet this same spacecraft, traveling at a speed that would vaporize you instantly upon contact with anything solid, would still require over 6,000 years to reach the nearest star. This is the barrier that will shatter everything you think you know about space travel. The distance a human could actually cross in a single lifetime is not limited by engineering, not limited by money, not limited by willpower. It is limited by a barrier woven into the fabric of reality itself. But here's what nobody tells you. Within that barrier lies a loophole so profound that it would allow you to reach places millions of light years away while aging only decades. Are you ready to discover exactly how far one human life can stretch across the cosmos? Then stay with me, because what comes next will change how you see the universe forever. The fastest object humanity has ever built, the Parker Solar Probe, launched in 2018, has achieved speeds exceeding 430,000 miles per hour during its closest approaches to the Sun. Picture this. At this velocity, the probe travels fast enough to cross the entire continental United States in under 25 seconds. Standing in New York, you could blink twice and this spacecraft would have already passed Los Angeles, continued over the Pacific Ocean, and be approaching Hawaii. This is not science fiction. This is happening right now. But think about what it took to reach this speed. Decades of technological development, billions of dollars in investment, the combined expertise of thousands of scientists and engineers. The Parker Solar Probe exploits a series of gravitational assists from Venus to accelerate to speeds no chemical rocket could ever achieve on its own. Each flyby steals a tiny amount of the planet's orbital energy, gradually building velocity over years of careful trajectory adjustments. This represents the absolute pinnacle of human engineering, our single greatest effort at moving fast through the cosmic void. And yet, as you're about to discover, this achievement is almost laughably inadequate for the task of interstellar travel. To appreciate how remarkable this speed truly is, consider the entire history of human velocity achievements. For most of our existence as a species, the fastest any human could travel was roughly 25 miles per hour, the top speed of a running horse. This limit persisted for over 200,000 years of human history, 200,000 years where our maximum speed barely exceeded a fast run. By 1900, automobiles pushed past 60 miles per hour. The Wright brothers flew at 34 miles per hour in 1903. Within 60 years, test pilots broke the sound barrier at 761 miles per hour. By 1969, Apollo astronauts returning from the moon achieved nearly 25,000 miles per hour, the fastest any human has ever traveled. The Parker Solar Probe moves 17 times faster than those Apollo astronauts. It travels at a velocity so extreme that no human could survive aboard it, not because of the speed itself, but because the trajectory passes close enough to the Sun to experience temperatures exceeding 2,500 degrees Fahrenheit. This is speed achieved through decades of gravitational ballet, not raw engine power. But here's where the crushing truth reveals itself. Even this extraordinary velocity exposes our cosmic limitations in the most brutal way imaginable, the Proxima Centauri paradox. Our nearest neighbor is impossibly far. At 430,000 miles per hour, the Parker Solar Probe would require approximately 6,600 years to reach Proxima Centauri. Our nearest stellar neighbor, sitting just 4.24 light-years away. Think about what this means in human terms. A journey beginning when the ancient Sumerians first invented writing would only now be approaching its destination. When your ancestors were carving the first letters into clay tablets, a spacecraft could have departed Earth. Every empire that has ever risen and fallen, every war ever fought, every human who has ever lived and died since the invention of writing, all of that history would unfold while this spacecraft crawls toward the nearest star. And it would only now be arriving. A human lifetime spans roughly 80 years. This means that traveling at humanity's current maximum speed, you could cover barely more than 1% of the distance to the closest star before your heart beat its final rhythm. 1%. After an entire lifetime of travel at record-breaking speeds, you wouldn't even be close to arriving anywhere. The mathematics become even more disturbing when you consider what one human lifetime actually accomplishes at these unprecedented speeds. Traveling continuously at the Parker Solar Probe's peak velocity for 80 years would carry you approximately 3 trillion miles. Written out completely, that number contains 12 zeros. It sounds unimaginably vast. 3 trillion miles. The human mind cannot truly comprehend such distances until you measure it against the true scale of cosmic distances. 3 trillion miles equals roughly 0.05 light-years. The nearest star system sits more than 80 times farther away than what an entire human lifetime at maximum velocity could cover. You would spend your whole existence traveling and never come close to leaving our stellar neighborhood. Your entire life dedicated to moving as fast as physically possible with current technology would be insufficient to escape our sun's immediate vicinity. But wait, it gets worse. The Oort cloud, the true prison walls of our solar system. The Oort cloud provides another sobering reference point that most people never hear about. This frozen spherical shell of ancient comets marks the outermost boundary of our sun's gravitational influence. It extends up to 100,000 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, roughly 93 million miles. The Oort cloud represents the true edge of our solar system, the point where the sun's gravity finally loses its grip and interstellar space truly begins. This is where our solar system actually ends, not at Pluto, not at Neptune, but out here in this vast frozen shell of debris, at humanity's current maximum speed. Reaching even the inner edge of the Oort cloud would require approximately 600 years of continuous travel. 600 years. An entire human lifetime at unprecedented velocities would not even escape our solar system's sphere of gravitational dominance. Think about this carefully. We would die long before leaving the sun's extended family of orbiting debris. Our entire existence of travel would accomplish less than crossing from Manhattan to Brooklyn. When measured against the true scale of even our local cosmic neighborhood, you see where this is going, don't you? The universe isn't just big. It's designed in a way that seems specifically calibrated to keep us trapped here. Voyager 1, 47 years of travel gets you nowhere. Consider the Voyager 1 spacecraft for perspective on what decades of actual space travel accomplish. This remarkable probe has traveled farther from Earth than any other human-made object in history. After more than 47 years of continuous journey through interplanetary and now interstellar space, Voyager 1 has covered approximately 15 billion miles. 15 billion miles. After 47 years, nearly half a century of continuous travel, Voyager 1 crossed the heliopause in 2012, officially entering interstellar space. This boundary marks where the Sun's solar wind loses its battle against the pressure of interstellar medium. The thin gas and dust that fills the space between stars. Headlines proclaimed that Voyager had left the solar system. Technically true in one sense, deeply misleading in another. The probe escaped the Sun's magnetic influence, but remains firmly within the Sun's gravitational domain. It will not pass beyond the Oort cloud for another 30,000 years. 30,000 years, think about that timeline. Modern humans have only existed for about 300,000 years. Voyager 1 will spend 1/10 of our entire species' existence just trying to leave our solar system's gravitational influence. 15 billion miles sounds impressive until you realize it represents less than 0.03% of the distance to the nearest star. If the journey to Proxima Centauri was scaled down to a cross-country road trip from New York to Los Angeles, approximately 2,800 miles of highway, Voyager 1 would have traveled roughly 100 feet in 47 years. Picture this. You would still be standing in your driveway, barely past the mailbox. After half a century of continuous driving, your neighbors would watch you age from youth to retirement while your car remained visible from their kitchen window. This is not an exaggeration. This is the actual scale we're dealing with. Here's another way to grasp this disparity. Light travels at 186,000 miles per second. In the time it took you to read this sentence, light traveled far enough to circle Earth 7 times. Voyager 1, after nearly 5 decades of travel, has covered a distance that light crosses in approximately 20 hours. The probe's 47-year journey equals less than 1 day of light travel. The 4-year journey to Proxima Centauri represents over 150,000 times more distance than Voyager has covered in nearly half a century. Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun. This velocity, while extraordinary by earthly standards, reveals the vast gulf between human achievement and cosmic requirement. At this speed, the probe would need over 70,000 years to reach Proxima Centauri. When Voyager 1 finally arrives at the distance of the nearest star, assuming it survives the journey through interstellar space, the humans who launched it will have been extinct longer than our entire species has currently existed. The probe will not survive that journey. Voyager 1 carries a plutonium power source that generates electricity through radioactive decay. This power source loses approximately 4 watts per year as the plutonium depletes. By 2025, the probe will lack sufficient power to operate any scientific instruments. By 2036, it will fall silent entirely, continuing its journey as a dead artifact tumbling through the void. It will drift for tens of thousands of years, a silent monument to human ambition, never reaching any destination, never being seen again by any human eye. The mathematical prison of chemical propulsion. The fundamental problem lies in the physics of chemical propulsion. Every rocket humanity has ever launched operates on the same basic principle that carried the first Chinese fireworks into the sky over 1,000 years ago. Hot gas expelled from one end pushes the vehicle in the opposite direction. Newton's third law, in elegant action: you throw mass backward and the reaction force pushes you forward. Simple, beautiful, and devastatingly limited, for the purposes of interstellar travel. Chemical rockets face an insurmountable barrier encoded in the Dzieciolowski rocket equation. This mathematical relationship, derived by Russian scientist Konstantin Dzieciolowski in 1903, governs the maximum velocity any rocket can achieve based on two factors. The first is the exhaust velocity of its propellant, essentially how fast the rocket can throw material out its back end. The second is the ratio between the rocket's initial mass, including all its fuel, and its final mass after burning that fuel. For chemical propellants, exhaust velocities max out around 4.5 kilometers per second. This is not an engineering limitation awaiting a clever solution. It is a fundamental constraint imposed by the chemistry of combustion itself. When you burn hydrogen and oxygen, the most energetic chemical reaction we can practically use for rockets, the resulting steam molecules can only move so fast. The energy released by breaking and forming chemical bonds has an absolute ceiling. No amount of engineering genius can make water molecules exit a rocket nozzle faster than chemistry permits. This is the universe telling us no. Not because it's cruel, but because this is how physics works. The tyranny of the rocket equation becomes horrifyingly clear when you calculate what reaching even modest interstellar velocities would require using chemical propulsion to accelerate a small probe weighing just 1,000 kilograms to 1% of light speed using chemical rockets. You would need a starting fuel mass exceeding the total mass of the observable universe. Read that again. Not the mass of Earth, not the mass of the Sun, not the mass of all the stars in our galaxy combined. The mass of every galaxy, every star, every planet, every atom in the entire observable cosmos would not provide enough chemical fuel to accelerate a small car to 1% of light speed. This is not hyperbole. This is not exaggeration for dramatic effect. This is what the mathematics actually demand. The rocket equation contains an exponential function that punishes any attempt to reach high velocities with chemical propulsion. Each additional increment of speed requires not just more fuel, but exponentially more fuel. The curve rises so steeply that it quickly exceeds any physically meaningful quantity of matter, which means chemical rockets, the only propulsion system humanity has actually mastered and deployed, are fundamentally incapable of interstellar travel. Period. End of discussion. Gravity assists, stealing energy from planets. Gravity assists provide some relief from this limitation, allowing spacecraft to steal energy from planets without burning fuel. By carefully timing flybys of massive bodies, a spacecraft can exchange momentum with planets, gradually accumulating speed through gravitational interactions. The Voyager probes used this technique extensively, bouncing from Jupiter to Saturn to build the velocities that carried them toward interstellar space. The Parker Solar Probe exploits multiple Venus flybys to accelerate toward its record-breaking speeds near the Sun. The mechanics of gravity assists involve falling toward a planet, gaining speed as gravity accelerates you, then leaving on a trajectory that converts some of the planet's orbital momentum into spacecraft velocity. The planet loses an imperceptible fraction of its orbital energy, while the spacecraft gains substantial speed. Jupiter moves slightly slower around the Sun after each Voyager flyby, though the change is far too small to measure. But even gravity assists have hard limits. The solar system contains only so many massive bodies positioned to provide useful acceleration. Jupiter represents our largest gravity assist resource, and spacecraft can only extract so much energy from each flyby. Each gravitational boost adds velocity at the cost of years of travel time to reach the next planetary encounter. a spacecraft designed specifically to optimize gravity assists, bouncing between planets over decades of careful maneuvering, might eventually reach velocities approaching 150,000 miles per hour. This represents roughly 4 times Voyager's current speed, achieved through a decade or more of patient trajectory planning. Still hopelessly inadequate for interstellar travel within any human time frame. Still requiring tens of thousands of years to reach even the nearest stars. The fastest outbound velocity any spacecraft has achieved primarily through gravity assists belongs to New Horizons, which flew past Pluto in 2015 at approximately 36,000 miles per hour relative to the Sun after receiving a massive boost from Jupiter in 2007. Even this impressive velocity would require over 80,000 years to cross the distance to our nearest stellar neighbor. 80,000 years. That's longer than modern humans have had agriculture. Longer than we've had cities. Longer than we've had written language. An entire human civilization from stone tools to space travel would rise and fall before the spacecraft arrived. So where does this leave us? Trapped, apparently. Chemical propulsion cannot get us there. Gravity assists help, but not nearly enough. Our fastest spacecraft would require longer than recorded human history to reach the nearest star, and a human lifetime at maximum velocity covers less than 1% of the journey. The universe seems to have imprisoned us on our homeworld through the simple mechanism of distance. The speed of light creates a barrier that no amount of clever engineering can overcome with conventional methods. We might communicate with distant stars through radio signals that take years to arrive, but we could never visit them. We could never walk on a world orbiting another sun. Or could we? What if I told you that hidden within the very equations that seem to imprison humanity lies a loophole so profound that it transforms everything? We think we know about the relationship between distance, time, and the limits of human exploration. What if the barrier isn't as solid as it appears? What if time itself is flexible? In 1905, a 26-year-old patent clerk in Bern, Switzerland, submitted a paper to a German physics journal. The paper bore an unassuming title that gave no hint of its revolutionary contents. On the electrodynamics of moving bodies. It contained no complex mathematics beyond algebra. It referenced almost no previous scientific literature. It was written by a man with no academic position, no laboratory, no research funding. Yet this single document would demolish 3 centuries of assumptions about how the universe operates. It would reveal that time itself bends to the will of velocity, and it would provide the key to unlocking interstellar travel within a human lifetime. Albert Einstein began with a premise so simple it seemed almost trivial. The speed of light in a vacuum remains constant for all observers, regardless of how fast those observers are moving. Whether you stand still on Earth or race through space at half the speed of light, you will always measure light traveling at exactly 6,282 miles per second. This constancy is not an engineering limitation, not a measurement artifact. It is woven into the fundamental structure of reality itself. But here's where everything breaks. If the speed of light must remain constant for all observers, then something else must give. That something turned out to be time itself. Einstein's revolution. Time is not what you think. Clocks aboard moving vessels tick slower than identical clocks remaining stationary. This effect, called time dilation, seemed absurd when first proposed. How could time, that most fundamental and universal of quantities, flow at different rates, depending on how fast you moved? Think about what this implies for a moment. Time, which we experience as this unchanging river carrying us all forward together. is actually flexible, malleable, dependent on your velocity through space. Two people can experience wildly different amounts of time passing while existing in the same universe. The mathematics proved inescapable. Within decades, experiments confirmed what Einstein had derived from pure logic. Time dilation is real. It is measurable, and it transforms everything we thought we knew about the limits of human exploration. The relationship between velocity and time dilation follows a precise mathematical formula. Einstein introduced a quantity physicists call gamma, the Lorentz factor. This number tells you exactly how much time slows down at any given velocity. The formula itself involves dividing 1 by the square root of 1 minus your velocity squared divided by the speed of light squared. The formula looks intimidating but yields numbers that change the fate of interstellar travelers. At everyday velocities, gamma barely differs from 1. A car traveling at highway speed experiences time dilation so minuscule that the most precise atomic clocks can barely detect it. An airplane passenger ages perhaps a few nanoseconds less than someone who stayed on the ground during a cross-country flight. The effect exists, but carries no practical significance for terrestrial life. The magic begins when velocity climbs toward a substantial fraction of light speed. And by magic, I mean the universe revealing its true nature in ways that defy human intuition. At 50% of light speed, gamma reaches 1.15. Time aboard the spacecraft passes about 15% slower than time on Earth. 1 year of ship time corresponds to roughly 14 months of Earth time. Noticeable, but not transformative. You'd age slightly less than people back home. But the difference wouldn't fundamentally alter the experience of space travel. But watch what happens as we push faster. The gamma factor, where physics gets weird. At 90% of light speed, gamma jumps to approximately 2.3. For every year that passes aboard the speeding vessel, 2 years and 4 months pass on Earth. This is where time dilation starts becoming significant. A 50-year journey at this velocity would see the traveler age 50 years while Earth aged 115 years. The crew would return to find their grandchildren, elderly, and their great-grandchildren running the world. Everyone they knew would be gone. The political landscape would be unrecognizable. Technology would have advanced far beyond what they left behind. They would be living fossils from another era. Pushed to 99% of light speed and gamma reaches 7.1. The transformation accelerates dramatically. 7 years pass on Earth for every year experienced by the traveler. A decade of ship time corresponds to 70 years of Earth time. A journey lasting 50 subjective years would span 355 years of Earth history. You would depart from one civilization and return to find an entirely different world. The United States would be older than it was when the trip began. Multiple generations would have lived and died. The very language might have evolved beyond easy recognition. At 99.9% of light speed, gamma exceeds 22. 22 years of Earth time compress into a single year aboard the spacecraft. The disparity has grown enormous. 50 years of travel would span 1100 years on Earth. The Roman Empire fell less than 1600 years ago. A journey of this duration would cross timespans comparable to the rise and fall of entire civilizations. Can you feel what's happening here? The universe is offering us a deal. Move fast enough, and you can cheat the distance problem. Not by moving faster than light, which remains impossible, but by changing how much time you experience during the journey. The mathematics continue relentlessly as velocity approaches light speed ever more closely. At 99.99%, gamma exceeds 70. At 99.999%, gamma surpasses 223. At 99.9999%, gamma climbs past 707. Each additional 9 added to the velocity pushes the time dilation factor higher by roughly a factor of 3. And this is where interstellar travel stops being impossible and starts being merely incredibly difficult. Practical applications: reaching the unreachable. Consider a journey not to the nearest star, but to somewhere more distant. Vega, one of the brightest stars in our night sky, lies approximately 25 light-years from Earth. At conventional spacecraft velocities, reaching Vega would require hundreds of thousands of years. No human could survive even a tiny fraction of such a journey. But at 99% of light speed, with gamma at 7.1, the calculation transforms completely. From Earth's perspective, the journey takes approximately 25 years and 3 months. Light speed is light speed and you cannot exceed it. But from the traveler's perspective, time dilation compresses this duration by a factor of 7. The subjective journey time drops to roughly 3.5 years. Read that again. 3.5 years. You could travel to Vega, spend time exploring any planets orbiting that brilliant blue-white star, and return to Earth having aged only 7 years, while 50 years passed at home. Your children would be middle-aged when you returned, but you would still be young. Push velocity to 99.9% of light speed, and the numbers become even more remarkable. Gamma, at 22, compresses that same 25-year journey to barely over 1 year of subjective time. You could visit Vega and return before your 2nd birthday aboard the ship. Earth would age 50 years during your round trip, but you would age only 2. This is not science fiction. This is verified physics. Time dilation has been measured countless times. It's real, it works, and it makes interstellar travel theoretically possible within a human lifetime. The Pleiades star cluster, that famous grouping of hot blue stars visible to the naked eye in winter skies, lies approximately 440 light-years from Earth. At conventional speeds, reaching the Pleiades would require millions of years. Multiple ice ages would come and go while your spacecraft crawled across the void. At 99.9% of light speed, with gamma exceeding 22, the subjective journey time drops to approximately 20 years. You could travel to one of the most famous star clusters in human mythology, explore multiple stellar systems within the cluster, and return having aged perhaps 40 years while Earth aged nearly 900 years. You would leave behind children and return to a world where your bloodline had continued for 30 generations, where your family name might still exist but attached to people who had no living memory of you, where history books would record your departure as ancient history, but you would have seen the Pleiades up close. You would have witnessed stars being born. You would have explored worlds no human had ever imagined. Would that trade be worth it? That's not a question physics can answer. That's a question only you can answer. The galactic center within reach. The center of our galaxy lies approximately 26,000 light-years away. A supermassive black hole containing 4 million times the mass of our Sun lurks there, surrounded by dense star clusters and violent phenomena found nowhere else in the Milky Way. At conventional speeds, the galactic center might as well be in another universe. At 99.999% of light speed, with gamma exceeding 223, the subjective journey time falls to approximately 116 years, still longer than a human lifetime, but within reach of a multi-generational crew, or travelers willing to accept life extension technologies that might emerge in coming centuries. Push to 99.9999% of light speed, with gamma exceeding 700, and the galactic center becomes reachable in approximately 37 years of ship time. A traveler could leave Earth at age 25, journey to the supermassive black hole at the heart of our galaxy, conduct observations impossible from Earth, and arrive having aged to 62. They would return to find that over 52,000 years had passed on Earth. 52,000 years. Modern humans have only existed for about 300,000 years. The traveler would return to find that roughly 1/6 of humanity's entire existence had elapsed during their journey. They would return to an Earth where their species might have evolved into something different, where civilization would have risen and fallen dozens of times, where no language they spoke, no culture they knew, no technology they understood would still exist. They would be more alien to Earth than any extraterrestrial visitor, but they would have seen the galactic center. They would have witnessed the monster at the heart of our galaxy. They would have explored a region of space that Earth-based telescopes can barely observe through the intervening dust and gas. Andromeda, the ultimate test. The Andromeda galaxy presents the ultimate test of relativistic travel within what we might call the local universe. At 2.5 million light-years distance, Andromeda represents the nearest major galaxy to our own. Its trillion stars form a spiral structure larger than the Milky Way, potentially harboring countless worlds and perhaps other civilizations. No conventional propulsion could ever bridge this gap within any meaningful time frame. The distance is so vast that it defeats imagination. 2.5 million light-years means light itself. Traveling faster than anything in the universe can travel requires 2.5 million years to make the crossing, yet at velocities where gamma reaches 1 million, achievable only at speeds so close to light that the difference becomes almost philosophical. The subjective journey time to Andromeda drops to approximately 2.5 years. 2.5 years. A traveler could cross the void between galaxies, explore an entirely separate island universe, and experience the journey as lasting less time than a typical doctoral program. Earth would age 2.5 million years during this journey. Human civilization would likely be unrecognizable or extinct upon return, but the traveler themselves would have aged only a few years. They would step out of their spacecraft in Andromeda, look up at unfamiliar constellations, orbit an unfamiliar galactic core, and exist impossibly distant from anything resembling home. They would see 1 trillion suns that no human eye had ever witnessed. They would explore worlds that Earth will never know about. Would you take that journey, knowing you could never truly return? Knowing that everyone and everything you knew would be dust long before you even finished your exploration of Andromeda? This is the bargain time dilation offers. Distance for connection, exploration for belonging, discovery for home. The twin paradox, proof that time bends. The twin paradox emerges naturally from these relativistic considerations and deserves careful examination because it illustrates just how profoundly time dilation affects human experience. Imagine 2 identical twins, Alice and Bob. Alice boards a relativistic spacecraft and travels to a star 20 light-years distant at 90% of light speed. Bob remains on Earth. From Bob's perspective on Earth, Alice's outbound journey takes approximately 22 years. Her return journey takes another 22 years. Bob ages 44 years waiting for his twin to return. Growing from a young adult to retirement age during Alice's absence, he watches his hair go grey. He feels his joints stiffen. He experiences every day of those 44 years. From Alice's perspective aboard the spacecraft, time dilation compresses each leg of the journey. At 90% of light speed, gamma equals approximately 2.3. Her 22-year outbound journey feels like only 9.5 years. Her return journey feels like another 9.5 years. Alice experiences only 19 years of travel, while Bob experiences 44. When Alice returns to Earth, she is 19 years older than when she left. Bob is 44 years older. The twins, who were born on the same day, are now separated by 25 years of biological age. Alice's hair might show the first hints of grey. Bob's has gone completely white. Alice might still be building her career. Bob is planning retirement. This scenario troubled early critics of relativity, who argued that motion is relative. From Alice's perspective, Bob was the one moving away and then returning. Why should Alice age less, rather than Bob? The resolution lies in the asymmetry of their experiences. Alice experienced acceleration when her spacecraft changed velocity. Bob experienced no acceleration. This asymmetry breaks the equivalence between their reference frames and determines who ages less. The twin paradox has been verified experimentally using precise atomic clocks. In 1971, physicists Joseph Haffel and Richard Keating flew cesium atomic clocks around the world on commercial airliners, comparing them to identical clocks that remained stationary. The flying clocks gained approximately 270 nanoseconds compared to the stationary clocks. Exactly as special relativity predicted, the effect was tiny because airplane velocities are tiny compared to light speed. But the effect was real, measurable, and it confirmed Einstein's century-old predictions. Time dilation is not theoretical speculation, it is experimental fact. We have measured it, we have verified it, we know it works. Why extreme velocities require extreme energy? But why do these extraordinary velocities require such extraordinary energy? The answer lies in another of Einstein's revolutionary insights, encoded in the most famous equation in physics. E equals mc squared tells us that mass and energy are equivalent, interchangeable aspects of the same underlying reality. This equivalence has consequences for anything attempting to move at relativistic velocities. As an object accelerates, it gains kinetic energy at low velocities. This energy increase follows familiar patterns Isaac Newton described centuries ago. Doubling your velocity quadruples your kinetic energy. The relationship is straightforward and places no fundamental limits on how fast you can go, provided you have enough fuel. But as velocity approaches a significant fraction of light speed, something strange happens. The energy required to accelerate further begins climbing faster than Newton's equations predict. Much faster. The object begins behaving as though it has more mass than it started with. At 50% of light speed, an object behaves as though it has about 15% more mass than it possesses at rest. The extra energy you pump in to accelerate further seems to disappear into this mass increase, rather than producing proportional velocity gains. At 90% of light speed, the effective mass has more than doubled. The same engine thrust that once produced rapid acceleration now yields sluggish response, as though the spacecraft had suddenly grown enormously heavy. At 99% of light speed, the effective mass has increased by a factor of 7. At 99.9%, the factor exceeds 22. Each increment of additional velocity requires not just more energy, but exponentially more energy. The relationship follows the same gamma factor that governs time dilation. But working against the traveler rather than for them, this mass increase explains why the speed of light represents an absolute barrier for any object possessing rest mass. As velocity approaches light speed, effective mass approaches infinity. Accelerating an infinite mass would require infinite energy. Since infinite energy does not exist, the final approach to light speed becomes asymptotic. You can get closer and closer, adding 9 after 9 to your velocity, but you can never quite arrive. The practical energy requirements for relativistic travel are staggering, even at velocities far below this theoretical limit. Consider accelerating a small probe massing perhaps 1,000 kilograms to 90% of light speed. The kinetic energy required exceeds 10 to the 19th power joules. Written out, this number contains 20 digits. It equals the total energy output of our Sun for approximately 2 seconds, or the entire energy consumption of human civilization for roughly 1 million years, concentrated into accelerating a single small spacecraft. For a crewed vessel capable of supporting human life during an interstellar journey, the mass might reach 100,000 kilograms or more. The energy requirement scales proportionally. Accelerating such a vessel to 90% of light speed would require energy equivalent to the Sun's total output for several minutes. This is not an engineering limitation awaiting a clever solution. It is a fundamental requirement imposed by the structure of spacetime itself. And here's the part that really hurts. The energy cost doubles when you remember that travelers generally want to stop when they arrive. Decelerating from 90% of light speed requires exactly as much energy as accelerating to that velocity in the first place. A round trip doubles the requirement again. A journey to Vega and back at 90% of light speed would require 4 times the energy needed for one-way acceleration, an amount exceeding the Sun's output for a quarter hour. These energy requirements explain why relativistic travel remains theoretical despite the physics being well understood for over a century. The acceleration profile, living through the journey. The acceleration profile for relativistic travel introduces additional constraints. Humans can tolerate continuous acceleration at 1 Earth gravity indefinitely. This feels like normal weight, allowing travelers to walk, eat, sleep, and function normally throughout the journey. Higher accelerations become uncomfortable and eventually dangerous. Sustained acceleration at 2 gravities causes fatigue and health problems. 5 gravities can cause blackouts. 10 gravities can be fatal. So we're limited to 1 gravity of continuous acceleration if we want travelers to arrive alive and functional. At 1 gravity of continuous acceleration, a spacecraft would reach 90% of light speed in approximately 11 months. The first half of this acceleration phase carries you toward your destination while building velocity. At the midpoint of your journey, you would flip the spacecraft and begin decelerating at 1 gravity, arriving at your destination with 0 relative velocity after the same duration of braking. 1 year of acceleration at 1 Earth gravity would bring a spacecraft to approximately 77% of light speed. 2 years would reach approximately 97%. 3 years would exceed 99%. The velocity gains slow as you approach light speed, with each additional year of acceleration adding smaller increments. But time dilation compensates, compressing the subjective journey time even as acceleration efficiency drops. The universe is giving with one hand while taking with the other. It becomes harder to accelerate as you go faster, but time slows down to compensate. It's almost as if reality is designed to make interstellar travel just barely possible for beings patient and clever enough to exploit these loopholes. So here's where we stand. Time dilation is real. It's been measured. It's been verified. It allows travelers to cross vast distances while aging minimally. The physics works. The equations are clear. Given sufficient velocity, a human lifetime could span distances that light itself requires millennia or millions of years to traverse. The barrier isn't physics. The barrier is engineering. We need to build engines that can reach these velocities. We need energy sources that can provide the stupendous power requirements relativistic travel demands. We need materials that can survive the radiation environment of near light speed travel. But it's possible. The universe hasn't locked us out. It's given us the key. Time dilation is that key. Now we just need to build the engine that turns it. The gap between current spacecraft velocities and the speeds necessary for interstellar travel within a human lifetime spans an almost incomprehensible gulf. Our fastest probes crawl through space at roughly 1/10,000th of light speed. Meaningful time dilation begins only above 10% of light speed and becomes truly transformative only above 90%. Crossing this velocity chasm requires propulsion concepts that transcend anything humanity has yet constructed, tested, or even fully designed. Consider the scale of the challenge. The Parker Solar Probe travels at approximately 0.06% of light speed during its closest solar approaches. Reaching 10% of light speed requires increasing velocity by a factor of roughly 170. Reaching 90% of light speed requires a velocity increase of 1,500 times beyond our current maximum. This is not an incremental engineering improvement. This is a revolution in propulsion technology that must bridge 6 orders of magnitude. And yet, humanity has conceived propulsion concepts that could potentially cross this gulf. Some require only engineering development using known physics. Others demand breakthroughs in materials, science, or energy production. A few push into speculative realms where the physics itself remains uncertain. But before we explore the impossible, let's examine what's actually possible with technologies we understand today. Nuclear pulse propulsion, riding nuclear explosions. Nuclear pulse propulsion represents perhaps the most audacious propulsion concept ever. Seriously studied by mainstream engineers, the idea emerged in the late 1950s at the General Atomics Laboratory in San Diego, where a team of brilliant physicists asked a question that seemed insane on its surface. What if you could harness nuclear explosions for spacecraft propulsion? What if, instead of containing nuclear energy within a reactor, you simply detonated bombs behind your spacecraft and rode the blast waves to the stars? Project Orion, as the effort became known, attracted some of the finest scientific minds of the era. Freeman, Dyson, Theodore Taylor, and dozens of other physicists and engineers devoted years to transforming this seemingly absurd concept into detailed engineering plans. They were not dreamers spinning fantasies. They were serious scientists, performing rigorous calculations and conducting actual experiments. The basic Orion concept works as follows. A spacecraft carries a large supply of nuclear explosive devices, essentially specially designed bombs. These devices are ejected one at a time from the rear of the spacecraft and detonated at a carefully calculated distance. The explosion creates a plasma fireball that expands outward in all directions. A massive pusher plate at the rear of the spacecraft absorbs the momentum from the fraction of this plasma that strikes it, pushing the vessel forward. Shock absorbers between the pusher plate and the crew compartment smooth out the violent impulses into tolerable acceleration. Here's what most people don't know. The Project Orion team conducted actual tests using conventional chemical explosives rather than nuclear devices. They built small models with pusher plates and detonated charges beneath them, demonstrating that the concept worked in practice. The models flew. The pusher plates survived repeated blasts. The shock absorption systems functioned as designed. Nuclear test ban treaties halted the program in 1963 before atomic detonations could be tested. but the physics had been validated. This wasn't theoretical. This was real hardware proving the concept worked. Calculations showed that Orion could achieve performance far exceeding any other propulsion concept then envisioned or since constructed. A modest Orion spacecraft using fission bombs could reach velocities of 3 to 4% of light speed. Larger designs incorporating hydrogen fusion bombs could potentially achieve 8 to 10% of light speed. The most ambitious designs, requiring engineering capabilities beyond 1960s technology, might reach 15% of light speed or higher. Think about what this means. At 10% of light speed, the journey to Tau Ceti, a sun-like star approximately 12 light-years distant that may host potentially habitable planets, would require roughly 120 years, still longer than a human lifetime, but within range of multi-generational missions, or travelers willing to spend most of their existence in transit. Time dilation at this velocity provides minimal benefit, compressing the journey by only about 0.5%. The spacecraft would experience essentially the same duration as observers on Earth measure, but you could actually get there within a time frame that's at least comprehensible to human minds. The engineering challenges for nuclear pulse propulsion remain formidable but not insurmountable. The pusher plate must survive repeated exposure to nuclear fireballs, temperatures of millions of degrees arriving in microsecond pulses thousands of times throughout the journey. Material science has advanced considerably since the 1960s, and modern composites and refractory metals could potentially meet these requirements. The shock absorption system must convert violent impulses into smooth acceleration without destroying the spacecraft or its occupants. This problem appears solvable with sufficient engineering effort. Carrying thousands of nuclear devices poses obvious dangers both during launch and throughout the journey. A catastrophic failure during Earth departure would scatter radioactive material across wide areas. An accident during flight could destroy the mission entirely. Yet nuclear pulse propulsion requires no new physics and no materials or technologies fundamentally beyond human capability. It represents the nearest term path to interstellar velocities using concepts we understand today. A more recent study called Project Longshot, conducted by the United States Naval Academy in 1987 and 88, examined a fusion-powered variant of nuclear pulse propulsion. This design would use small fusion explosions rather than fission bombs, achieving higher efficiency and reducing the radioactive hazard. Longshot was designed to reach Barnard's star, approximately 6 light-years distant, in roughly 100 years at approximately 4.5% of light speed. The study concluded that such a mission was technically feasible using technology that could be developed within decades. So why haven't we built it? Politics, public fear of nuclear technology, the enormous cost of development, the lack of any immediate practical application that would justify the investment. But the engineering is sound. The physics is proven. We could build a nuclear pulse spacecraft if we decided it was worth the money and the risk. Ion engines. Patience rewarded. Ion propulsion systems offer marginal improvements over chemical rockets by dramatically increasing exhaust velocity. These engines work by ionizing a propellant, typically xenon gas, and accelerating the resulting charged particles through electric fields. The ions exit the engine at velocities 10 to 20 times higher than chemical exhaust, allowing far greater efficiency in converting propellant mass to spacecraft velocity. The Dawn spacecraft used ion propulsion to explore the asteroid belt, becoming the first mission to orbit 2 different celestial bodies beyond Earth. Its ion engines allowed maneuvers that would have been impossible for chemical rockets of similar mass. The spacecraft could change its orbit gradually over months of continuous thrust, accomplishing trajectory alterations that chemical rockets could never achieve with available fuel. But here's the brutal truth about ion engines. They produce thrust so minuscule that their advantages evaporate for rapid acceleration. Don's ion drive generated approximately 90 millitons of force. To understand how small this is, hold a single sheet of paper flat on your palm. The weight of that paper pressing down equals roughly the thrust of an ion engine. This tiny force applied continuously for years can build significant velocity. But building that velocity requires patience measured in decades, not the days or weeks of chemical rocket burns. Even with unlimited fuel and a century of continuous operation, ion propulsion cannot approach the speeds necessary for interstellar travel within human timescales. You could run an ion engine for an entire human lifetime and still not reach velocities that would meaningfully reduce journey times to nearby stars. The technology excels at efficient maneuvering within our solar system but offers no solution to the interstellar distance problem. Ion drives are remarkable for what they do, but what they do is not enough. Nuclear thermal rockets, doubling down. Nuclear thermal rockets represent the next step up the propulsion ladder. These engines work by passing hydrogen propellant through a nuclear reactor, heating it to extreme temperatures before expelling it through a nozzle. The nuclear heat source allows the hydrogen to reach velocities roughly twice those possible with chemical combustion, effectively doubling the exhaust velocity and dramatically improving the rocket equation's cruel mathematics. NASA tested nuclear thermal rockets extensively during the NERVA program throughout the 1960s and early 1970s. Engineers conducted dozens of successful reactor tests, running nuclear engines for extended periods and demonstrating that nuclear thermal propulsion works reliably. The technology was mature enough for deployment before political and budgetary considerations ended the program in 1973. We have known how to build nuclear rockets for over 50 years but chose not to. Think about that for a moment. We had working nuclear rocket engines half a century ago, engines that performed exactly as designed, engines that could have opened the outer solar system to human exploration. And we abandoned them because of political decisions, not technical failures. A nuclear thermal rocket could theoretically accelerate a spacecraft to approximately 100,000 miles per hour with reasonable fuel ratios. This velocity represents a significant improvement over chemical systems, roughly tripling what we can achieve through combustion alone. The journey time to Proxima Centauri at this speed would drop to approximately 28,000 years. Still impossibly long for any individual human, still longer than recorded human civilization has existed. But progress nonetheless. Progress we chose to abandon. Solar sails, riding starlight. Solar sails represent perhaps the most elegant propulsion concept, exploiting the radiation pressure of sunlight itself to accelerate spacecraft without carrying any fuel whatsoever. When photons strike a reflective surface, they transfer tiny amounts of momentum, pushing the surface in the direction the light was traveling. A sufficiently large and lightweight reflective sheet could harness this pressure to gradually build velocity over time. The Japanese Icarus spacecraft demonstrated solar sail technology in 2010, successfully unfurling a 14-meter membrane and achieving measurable acceleration from sunlight alone. The probe proved that the concept works in practice, not just in theory. Light can push objects through space, and sufficiently advanced sails could exploit this effect for propulsion without carrying a single gram of fuel. Close to the sun, where radiation intensity reaches its peak, A solar sail could theoretically accelerate at rates approaching 1% of Earth's surface gravity. This sounds impressive until you realize that maintaining this acceleration requires staying near the sun, and the entire point of propulsion is to go somewhere else. As the sail moves away from the sun, radiation intensity drops with the square of distance. Double your distance from the sun and you receive only 1/4 of the radiation pressure. The acceleration that seems promising near the sun quickly becomes negligible in the outer solar system and vanishes entirely in interstellar space. A solar sail launched from a close solar approach might reach velocities of several 100,000 miles per hour before radiation pressure becomes too weak to provide meaningful acceleration. At 500,000 miles per hour, roughly 100 times Voyager's current velocity and faster than any spacecraft has ever traveled, the journey to the nearest star would still require over 5,000 years. A human lifetime at this speed would cover approximately 350 billion miles, or about 0.6 light-years. You could travel roughly 1/7 of the way to Proxima Centauri. Impressive progress, but you would still die in the void between stars, never reaching your destination. Fusion propulsion, the realistic frontier. Fusion propulsion represents perhaps the most realistic path to velocities where time dilation becomes meaningful for human travelers. Fusion reactions combine light atomic nuclei, typically isotopes of hydrogen, releasing energy far exceeding chemical or fission reactions. The sun itself is a fusion reactor, combining hydrogen into helium and radiating the energy that makes life on Earth possible. Harnessing this same process for propulsion could open the stars to human exploration. The physics of fusion propulsion is well understood. When deuterium and tritium nuclei fuse, they produce helium and a high-energy neutron, releasing approximately 17.6 million electron volts of energy. This vastly exceeds the few electron volts released by chemical reactions. A fusion rocket could theoretically achieve exhaust velocities of 3 to 5% of light speed, enabling spacecraft acceleration to 10 or 15% of light speed with reasonable fuel ratios. Project Daedalus, conducted by the British Interplanetary Society from 1973 to 1978, produced the most detailed engineering study of a fusion-powered interstellar probe. The design called for a 2-stage spacecraft burning pellets of deuterium and helium-3 through inertial confinement fusion. Powerful electron beams would compress fuel pellets until fusion ignited, expelling the reaction products through a magnetic nozzle. Daedalus was designed to reach Barnard's star, approximately 6 light-years distant, in approximately 50 years at a cruise velocity of 12% of light speed. The first stage would burn for 2 years, accelerating the spacecraft to 7.1% of light speed before separating. The second stage would continue acceleration for another 1.8 years, reaching final velocity before coasting to its destination. The spacecraft would be enormous by any standard, massing approximately 54,000 tons at launch. With the vast majority being fuel, it would carry no deceleration system, instead flashing through the Barnard star system at 12% of light speed while conducting observations during its brief passage. The probe would continue into interstellar space forever, its mission completed in the few days it spent traversing its target system. Project Icarus, initiated in 2009 by the British Interplanetary Society and the Tau Zero Foundation, revisited the Daedalus concept with updated physics and engineering assumptions. Icarus studies explored various fusion fuel combinations and engine configurations, generally confirming that velocities between 10 and 20% of light speed appear achievable with fusion propulsion using technology that might be developed within the coming century. At 15% of light speed, the journey to Sirius, the brightest star in Earth's night sky at 8.6 light-years distance, would require approximately 57 years from Earth's perspective. Time dilation at this velocity compresses the traveler's experience by roughly 1%, providing minimal benefit. A human departing Earth at age 25 would arrive at Sirius at age 82, having spent essentially their entire adult life in transit. This represents survival but hardly practical interstellar travel. You'd be an old person arriving at a new star system with most of your life spent in a metal tube hurtling through the void. The Bussard ramjet. Beautiful theory, broken reality. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, offered an elegant, theoretical solution. Instead of carrying fusion fuel, a ramjet would scoop hydrogen from the interstellar medium using enormous magnetic fields, fusing this collected material to generate continuous thrust. In principle, a Bussard ramjet could accelerate indefinitely, harvesting fuel as it traveled and limited only by relativistic mass increase as it approached light speed. The concept inspired decades of science fiction and serious scientific study. It seemed to offer a pathway to true relativistic travel without the fuel mass penalties that limit conventional rockets. Engineers designed magnetic scoops thousands of kilometers across. They calculated fusion rates and thrust profiles. They dreamed of starships that could cruise at 90% of light speed or higher, powered by the cosmos itself. Detailed calculations eventually revealed fatal problems with the ramjet concept. The interstellar medium contains approximately 1 hydrogen atom per cubic centimeter on average, far less in some regions and more in others. Collecting enough hydrogen to sustain fusion requires a magnetic scoop measuring thousands of kilometers across. But this enormous scoop interacts with the charged particles it collects, creating drag that exceeds the thrust the fusion drive can produce. The ramjet essentially creates a parachute larger than the engine can overcome. You'd slow down rather than speed up. The very mechanism meant to gather fuel would prevent you from going anywhere. More recent analyses have shown that the concept might work in unusually dense regions of interstellar space, such as within giant molecular clouds, but fails in the typical interstellar medium. The dream of unlimited relativistic acceleration through fuel harvesting appears physically impossible with understood physics. The ramjet remains one of the great disappointments in propulsion theory, a concept so elegant, so promising, so perfectly suited to interstellar travel, and fundamentally broken by the realities of physics. The brutal assessment. This is the devastating reality of current and near-future propulsion technology. The fastest speeds achievable through any mechanism humanity has demonstrated, tested, or could plausibly construct within the next century cannot carry a human being beyond our immediate cosmic neighborhood within their natural lifespan. Chemical rockets are fundamentally incapable. Ion engines are too weak. Nuclear thermal rockets help, but not nearly enough. Solar sails cannot accelerate large masses to sufficient velocities. Fusion propulsion gets us into the 10 to 20% of light speed range, which sounds impressive until you realize time dilation doesn't really kick in until you're above 50%. We remain trapped, seemingly permanently, within a few light hours of our home world. The psychological weight of this limitation shaped early scientific attitudes toward interstellar travel. Many 20th century physicists considered travel between stars to be physically impossible for biological beings. The energy requirements seemed astronomical. The journey times exceeded any reasonable definition of practical, but hidden within the very equations that seem to imprison humanity lies potential we haven't yet harnessed. The physics permits relativistic travel. We simply lack the engineering to achieve the necessary velocities. The barrier is not nature. The barrier is us. Our limited understanding, our limited resources, our limited commitment to solving the hardest problems. The question becomes whether we'll ever develop the technologies necessary to exploit time dilation, whether humanity will invest the centuries of research and trillions of dollars necessary to build engines that can reach 90% of light speed, whether we have the collective will to pursue a goal whose benefits won't materialize for generations, or whether we'll remain forever trapped in our solar system, looking out at stars we can see but never touch, wondering what might have been if we'd been just a little bit bolder. More speculative propulsion concepts venture into physics that remains theoretical or entirely hypothetical. Some exist only as mathematics on paper, others require materials that may not exist in nature. A few demand energy scales that dwarf anything humanity has ever harnessed, but they represent the frontier of what might be possible if we're willing to push the boundaries of known physics. Antimatter propulsion, perfect fuel, impossible production. Antimatter propulsion occupies a unique position among interstellar concepts, offering energy density that dwarfs all other known fuel sources while remaining grounded in well-understood physics. When a particle of matter contacts its antimatter counterpart, both annihilate completely, converting 100% of their combined mass into energy. This compares to nuclear fission, which converts roughly 0.1% of mass to energy, and nuclear fusion, which achieves approximately 0.7% conversion. Antimatter is roughly 140 times more energy dense than fusion and 1,000 times more efficient than fission. A single gram of antimatter annihilating with a gram of normal matter releases approximately 180 trillion joules of energy. This equals the explosive yield of the Hiroshima atomic bomb. It represents the energy consumption of an average American household for 4.5 years. It could accelerate a small spacecraft to velocities that chemical rockets could never approach, regardless of their fuel supply. The energy density of antimatter makes it theoretically ideal for bridging the velocity gap to relativistic speeds. An antimatter rocket would work by directing the products of matter-antimatter annihilation through a magnetic nozzle to generate thrust. The exhaust velocity of an antimatter rocket approaches a significant fraction of light speed itself, vastly exceeding what any chemical, nuclear, or fusion system can achieve. Consider a journey to Epsilon Eridani, a young, sun-like star approximately 10.5 light-years from Earth that hosts at least one confirmed planet at 30% of light speed, achievable with approximately 100 kilograms of antimatter for a modest probe. The journey would require roughly 35 years from Earth's perspective. Time dilation at this velocity compresses the traveler's experience to about 33 years. Several thousand kilograms of antimatter could theoretically accelerate a crewed vessel to 70 or 80% of light speed at these velocities. The journey to Epsilon Eridani would still require approximately 13 to 14 years from Earth's perspective, but time dilation would compress the traveler's experience to 8 or 9 years. The insurmountable obstacle with antimatter propulsion lies not in the physics, but in the production. Antimatter does not exist naturally in significant quantities anywhere in the known universe. Every antipraton used for propulsion must be manufactured through particle accelerator collisions that require enormous energy inputs. Current global antimatter production totals perhaps 10 to 20 nanograms per year. generated primarily at facilities like CERN in Switzerland and Fermilab in the United States. To appreciate how minuscule this production rate is, consider that reaching epsilon Eridani with 100 kilograms of antimatter would require accumulating current global production for approximately 5 billion years. The energy cost compounds this problem catastrophically. Creating antimatter through particle collisions consumes roughly 10 billion times more energy than the antimatter ultimately stores. Manufacturing enough antimatter for a single interstellar probe would require energy inputs exceeding total human civilization's power consumption for centuries or millennia. Antimatter storage presents equally daunting challenges. Antimatter annihilates instantly upon contact with normal matter, requiring containment systems that suspend the fuel in perfect vacuum using magnetic fields. The fuel must never touch the container walls, must remain stable during launch vibrations, and must survive decades of storage during interstellar transit. The longest antimatter has been successfully stored is approximately 16 hours, achieved at CERN in 2023. Scaling from 16 hours to decades represents an improvement factor of roughly 10,000. These production and storage challenges relegate antimatter propulsion to the distant future, if it ever becomes practical at all. The physics works beautifully. The engineering remains beyond any foreseeable capability. Antimatter represents a theoretical ideal against which other propulsion concepts can be measured, but not a near-term pathway to the stars. Beamed energy propulsion. Leave the power at home. Beamed energy propulsion sidesteps the fundamental problem plaguing all rocket-based concepts. Rockets must carry their energy source with them, and that energy source has mass that must itself be accelerated. This creates a vicious cycle where adding fuel to increase velocity also adds mass that requires yet more fuel to accelerate. Beamed energy systems break this cycle by leaving the power source at home. The concept traces back to the 1960s, when physicist Robert Forward proposed using powerful lasers to precessalate lightweight solar sails to interstellar velocities. A sail need carry no fuel at all. It accelerates by reflecting photons, gaining momentum from light itself. Breakthrough Starshot, announced in 2016 with $100 million in initial funding from Russian billionaire Yuri Milner, represents the most serious modern effort to develop beamed energy propulsion. The project, endorsed by the late Stephen Hawking before his death, proposes using a ground-based laser array to accelerate tiny spacecraft, called starships, to 20% of light speed. At this velocity, the journey to the Alpha Centauri system would require approximately 20 years. The breakthrough Starshot concept envisions a phased array of lasers with combined power output approaching 100 gigawatts, roughly equivalent to the electrical output of 100 large nuclear power plants. This array would focus on a spacecraft massing only a few grams, consisting of a reflective sail measuring perhaps 4 meters across, connected to a tiny chip carrying cameras, communication systems, and navigation equipment. The intense photon pressure would accelerate this gossamer vessel from rest to 20% of light speed in approximately 10 minutes. The engineering challenges are staggering but potentially surmountable. The laser array must maintain coherent focus on a target accelerating away at enormous rates, eventually receding to distances where light speed delays between the laser and its target stretch to seconds and then minutes. The sail must survive radiation intensities that would vaporize conventional materials, requiring advanced reflective coatings that remain speculative. The tiny star chip must contain functional scientific instruments despite massing less than a standard paperclip, yet breakthrough Starshot offers genuine advantages over other interstellar concepts. The laser array remains on Earth, where it can be powered by terrestrial energy sources, maintained, upgraded, and reused for multiple missions. Each individual starship costs relatively little compared to conventional spacecraft, allowing hundreds or thousands to be launched. The fatal limitation of beamed energy propulsion for human travel lies in deceleration. A laser-propelled sail accelerates by reflecting light from behind. It cannot slow down using the same mechanism because no laser exists at the destination to push back against. A breakthrough Starshot probe would flash through the Alpha Centauri system at 20% of light speed, having mere minutes to conduct observations before departing forever. 4 robotic probes seeking photographs. This might suffice. For human travelers wishing to stop and explore, this approach fails completely. Am Ende des Reide bleibt ein leiser, aber kraftvoller Gedanke, selbst wenn wir noch nicht ankommen können, haben wir bereits gelernt, wie man die Grenzen berührt. Zwischen dem, was technisch, ungleich scheint, und dem, was eines Tages Realität wird, liegt genau dieser Moment des Staunens. Lass in MIT, dir in die Nähont gehen, gut nähot. Und dir wisst ja, Jed, nohud not, kommen wir den Geheimnis, wollen Rotzelne, Universums einen Schritt näher, vergisst nicht, den Kanalzu, abonnieren, keine Sendung zu verpassen, vielen Dank, und ein gut, ruhig, no hit.